Good afternoon, everyone. Thank you all for coming to another Compass Wednesday and for being here for Lisa's talk. We have a full room. That's so exciting. Let's continue this entire semester. I'm proud to introduce Lisa today. She's a professor in the Ocean Sciences Department, teaching physical oceanography classes. She's my advisor. Lisa has been here at the Rosenstiel School, I think, since 2005. Am I wrong?
2003.
2003, sorry. And she's an expert in the Agulhas system of currents around South Africa and has brought recognition to the key role this system plays in a warming climate. She designs research programs, leads scientific cruises, and supervises an awesome lab of graduate and postdoc students in a quest to better understand the ocean. In addition to her research, Lisa works to increase engagement, recruitment, and retention of women and minorities in oceanography. She funds and co-leads an annual scientific writing workshop with author Dallas Murphy that all grad students should take if they have the chance. And she currently serves as editor-in-chief of JGR Oceans, where she's proud to have recruited the most diverse editorial board in the journal's history. When she's not being an oceanographer, a mentor, a teacher, a writer, a chief scientist, an editor, a communicator, or a climate action advocate, Lisa is an open water swimmer, a tango dancer, and a proud member of the LGBTQ community. She loves fresh cocktails, the performing arts, and hanging in the shady wild garden she shares with her neighbors in Miami Beach. So let's welcome Lisa for her talk on more eddying in subtropical western boundary currents.
What an awesome introduction. I think that was stolen from the She Rose thing. But, okay. Well, thank you all for coming. It's a provocative title, right? So I'm glad you all came to be interested in what might be happening to subtropical western boundary currents with climate change. And as Paloma said, I've spent most of my career working on the Agulhas Current, working on western boundary currents and the Agulhas Current in particular. And so this work is just kind of the latest in many years of work and draws on all those years of work. And so in that case, I'm going to say thank you at the beginning because I don't want to forget. In particular, this work is with Kathy Gunn here, who's now moved on to the University of Southampton. Kathy was a postdoc in my group a few years ago. Kay McMonigal and Shen Elapo contributed a lot to the groundwork of this latest research and a lot to past research in the Agulhas Current. And Juliette Hermes is our collaborator in South Africa. Without her, we couldn't have done the final array that we had in the Agulhas Current. It was a joint endeavor with South African Ship Time. And this is my group, plus the two technicians at OTEC who make all this wonderful science possible right now. So thank you, guys. And we have an additional group member who we need to take a new picture. So what got me interested quite a few years ago now in thinking about how western boundary currents were changing with climate change, in particular was this picture. So this is sea surface temperature trend minus the global trend from the HAD2SST data set. And you can see that the western boundary current regions, this is the Gulf Stream region, this is the Kuroshio region, this is the Agulhas and the Agulhas return current region, the Brazil current, and so on, East Australia current, all the world's subtropical western boundary currents really light up as regions that are warming at about 2 to 3 times the rate of other parts of the globe, not including the Arctic, notably, because the Arctic is warming extremely fast as well. So this brought on a slew of research, this paper, and some papers have since said, well, this is because the western boundary currents are strengthening. They're somehow carrying more heat away from the tropics towards the poles, and this is causing all this warming. And together with that, maybe there's a shift poleward also of some of these subtropical fronts. This seems particularly robust maybe in the southern hemisphere. But then some papers are finding that, in fact, some of these western boundary currents are weakening, right? While others are strengthening. And Beal and Elipo, myself in the Agulhas Current, and recently Denis Volkov in the Gulf Stream, some are holding steady. And these are observations, right? And there seems to be more and more pointing to the fact that they're not changing in strength. So it's hard to make sense in terms of total volume transport, in terms of just talking about the strength of the current, what's happening, why these regions are warming so quickly, why these frontal regions are warming so quickly. And so the hypothesis in this talk is that it's all about the eddies. So some of the data that's gone into this, I'm going to start off with just reviewing some kind of bullet points of former work that kind of go into the interpretation of this work. And these former works were based on 2 tall mooring arrays that were out in the Agulhas Current for a total of 5 years, not consecutively. There was a gap between, so we had what we called ACT, that went on from 2010 to 2013, and in ACT we measured velocity. And then we had another array, ASCA, 2016 to 2018, in collaboration with the South African government, and we measured velocity, temperature, and salinity during that time. Both these arrays were in the exact same geographic location, and here it is. It's coming off the South African coast here, off the Southeast Cape in the Indian Ocean, where the Agulhas Current, of course, passes by. And we had an array of 7 tall moorings, A through G, and we had these CPIs offshore. They're just bottom instruments that allow us to collect something about the water column without having the expense of a full tall mooring. And we're mostly going to talk about these tall moorings today, A through G, and you'll notice that A is closest to the coast and G is farthest offshore, and this distance is about 200 kilometers. The other thing to notice is that we put this array along a satellite ground track. So these green dashed lines are altimeter tracks, and those ground tracks have been occupied by altimeter consistently since 1993. And so we were able to leverage some of that information to basically expand our in situ observations over time and try to imply what might be happening on the longer timescales. Okay. So here's just a little quick look at some of the instrumentation. We used point acoustic current meters. The current meters nowadays, they all measure the ocean with acoustics using Doppler shift. And these ones have, they measure about a meter out from the instrument here, and they measure just one single point. On the top of each mooring, we had these 75 kilohertz ADCPs, which can insonify all the way from the top buoy here upward in the water column, the upper 500 meters of the water column. We also had, in the second array, we added microcats. These are basically like CTDs. They measure temperature and salinity. And these are the CPIs that we had on the offshore end of the array. And I should have mentioned, the reason we had these CPIs out here is because sometimes the Agulhas Current meanders. It meanders so much that it detaches completely from the coast, and those meanders have about 100 kilometer amplitude. And so this is the mean current, this is the mean flow here from our second set of observations. But you'll see that sometimes this flow could move out over and further offshore than G. So we didn't want to miss the transport, miss the current when it was out there, and so that's why we had the CPIs. And then of course I've included, this is the JSON 3 version of the NASA altimeter. Okay, so previous work with the first set of mooring data, just velocity, we found that the Agulhas Current was broadening and not strengthening. How did we find that? We had mooring observations in this time frame, and we calculated a volume transport for the Agulhas Current going through this array every day. And we did that in a streamwise fashion in red. So that was following the jet. So if it meanders offshore, we go with it. And we just count southwest transport. And then we did a Cartesian version where we just calculated the transport from the coast to the mean zero ice attack position. Okay? So a streamwise transport, a Cartesian transport. No matter which way you do it, there's no significant trend. Okay, we took these observations, and I don't have time to go into the details of it, but we built a proxy. Shen did the hard work of this. He used the sea surface height data, and he fitted it to every mooring data. So we had a proxy not just for the bulk transport, but for the transport per unit distance at every mooring, okay, so that we could look at not just the variability of the volume transport as a pulse, but also the variability of the current on and offshore. What we found is that although the transport is steady, you get a pattern where, and this is the trend of the surface slope from the satellite data, and this is the trend of the transport from the in situ data. And what you can see in this surface slope trend is that you have a negative slope trend inshore of 100 kilometers, and you have a positive slope trend offshore. And what that means is that you have, if you look between the first 5 years, the solid lines, and the last 5 years, the dashed lines, you see how the dashed lines are smaller in the middle of the jet, in the current core, and larger offshore. So the transport's decreased, it's weakened in the center of the jet, and it's broadened the jet offshore, okay? And if we looked at, we were like, well, how can that be happening? What is this broadening about? If you look at the eddy kinetic energy, what you see is, and this is just the mean, the eddy, and the total kinetic energy across the current, and you can see the peak here at the core of the current. The yellow is the eddy kinetic energy, and if you look at the trends of these, you've got a positive trend in eddy kinetic energy everywhere across the array, okay, over this proxy timescale, 20 years. So we interpreted that the current is broadening because it's eddying more. And we interpreted eddying in terms of meanders, because that's mostly what you see when you look at the Agulhas, is these huge meanders. Here's an example of one. In sea surface temperature, it's hard to get sea surface temperature because it's often cloudy. But you can see this is the leading edge of a meander here, and you can see some intrusion on shore of warm, salty water from the Agulhas Current. And this is kind of in the trough of a meander, and you've got all this cold water onshore, right? If you look at how many meanders you get in time, we did an update of this since Shen and I looked at it back in 2015, and there's still an increase in time, a significant increase in the number of these solitary meander events in the Agulhas Current. They happen between 0 and 3 times a year. Okay. So meanders, you'll notice, they're associated with both warm and cold anomalies, right? We've got this warm anomaly happening here, we've got this cold anomaly happening here. If you look in cross-section, you can see here the density surfaces or the temperature surfaces are downwelling here and upwelling here, right? So the question is, well, let's hold that question. let's look first at one other piece of previous work, because this is relevant to those sea surface temperature trends we were looking at. So Kay McMonigal led this work when he was a student here. He's now at University of Alaska in Fairbanks. And we wanted to know, okay, what's the downstream effect potentially of more meanders, right? So he calculated the transport weighted temperature. He calculated the temperature transport of the Agulhas Current. And what we're showing here is the transport weighted temperature. So you can think of that as if you add up V and T across the whole array, and then you divide that by the total transport, you get a transport weighted temperature. And it kind of gives you a bulk idea of whether the current is cooling or warming, whether it's anomalously cold or anomalously warm at any moment in time. And what we found is that during meanders, we had a transport weighted temperature that was massively cooler. And he went on to show that, in fact, the meridional heat transport of the Agulhas Current has reduced. And this is consistent with other research across the Indian Ocean basin as a whole, actually, that's been showing the Indian Ocean as a whole has been warming rapidly, and a lot of that warm water is collecting on the southern extent of the subtropical gyre. But what's interesting is that, right, there's also warmer surface waters. So you get this impression of an uplift of the isotherms onshore here, and perhaps a depression offshore here. So you've got cooling and warming going on here, right? It's not kind of it's what we're going to see. It gets quite complex. But top to bottom, overall, the transport weighted temperature is cooler and the meridional heat transport is reduced. And Kay did this by adding a whole interior Indian Ocean section using Argo floats. So this is the mass conserving meridional heat transport in the Indian Ocean has reduced. So at the same time, the surface waters appear warmer, and that could be consistent with our SST signal, right? So remember, we've got these rapidly warming SSTs, but now we've got a reduction in the heat transport. That seems weird, but at the same time, we've got surface waters that appear warmer. Okay, so this brings us to the current work on eddy fluxes. So we wanted to go, beyond just this kind of characterization of what meanders do or do not do, and do a better accounting of the full impact of all the eddying in the Agulhas Current, right? So what we did was we calculated what's called the divergent eddy fluxes. Divergent eddy fluxes, so if you do the Reynolds separation, the first thing you get is your U prime, T prime, and that's just the fluctuating velocity and the fluctuating temperature from a mean, right? In this case, just a record mean. But if you calculate that, then included in that fluctuation is eddies that may just circulate the heat and end up back where it started, right? So, and this is often called the rotational component. And so Marshall and Schutz, they estimated the rotational component using this eddy entropy term. And we did it another way. We used Bishop et al., which is rather simpler. He uses largely barotropic bottom velocities. But either way, we end up with a divergent eddy flux that looks like this over time. So we get an eddy flux. You can see that we've marked the center of the current here, and you've probably seen it move around a bit during the meanders. But what you'll also see is that there are eddy red is onshore warm, and blue is onshore cold. And you'll see that there are eddy fluxes occurring not just when the current is meandering, right? There's other eddying motions going on that can create quite large fluxes. These are salinity fluxes, and these are the temperature fluxes. So these are all cross-shore now, right? So we're not thinking about the downstream transport, we're thinking about how the eddies themselves are changing the structure of the current, and also potentially the shelf seas adjacent to the current. Okay, of course there are some uncertainties in this work. The upper ocean temperature and salinity are rather sparsely observed. You can see from the arrays we had these, we call them microcap tails, up above the major top float. We had 4 of those, and that's where we got our temperature and salinity. But we often also got a lot of blowdown with these moorings, and which took our observations away from the surface even more. So we had to fill in some gaps in the upper there, and we used satellite data at the surface to do that. That means the subsurface salinity maximum of the subtropical waters is poorly resolved. And we extrapolate over the shelf. So everything inshore of A is extrapolated. We were supposed to have some coastal moorings, but we never got any of them back. And the net fluxes are 1/10 of the instantaneous. So we're going to go on to look at the tendency of these eddy fluxes, like what the eddy fluxes are doing over time to the flow. And we're going to remember that those tendencies are very small. But hopefully I'm going to convince you, because of so much consistency among all these things that we're looking at, that it's real. Okay. So if we look at those cross-shore eddy fluxes that I was showing the movie of, and we look at how the instantaneous eddy fluxes vary in time, we get this kind of picture. And we got a different curve, a different color for every one of the moorings. I've put a little crib up here. You'll notice that A is the only mooring that always sits on the onshore side, or the cyclonic side, the cyclonic velocity shear side of the current, okay? And I have drawn these exactly the wrong way around. Yeah. This is because this is the southern hemisphere, right? So this is cyclonic, my apologies, and this is anticyclonic. You can see from the tendency of the shear, right? Ignoring okay. So A is on the cyclonic side, all the others are on the anticyclonic side. That becomes important because once we start looking, so what you see in the instantaneous is a lot going on, but it's hard to tell, what's happening over time, right? You can see that there are periods when there are a lot of eddy fluxes, and there tends to be a positive flux followed by a large negative flux. Okay. If we look at the cumulative fluxes, now we start to get some tendencies, and you can see that the tendencies are very different depending on which side of the current you're on. So if you are on the offshore anticyclonic side, then the eddy fluxes tend to be onshore warm and salty. So it's moving warm and salty water towards the coast. And if you're on the onshore side at A, then you tend to be moving heat and salt offshore. Okay, and the implication for that is that you're cooling the adjacent shelf seas. Hence, the eddies tend to accumulate heat and salt at the core of the current.
Hey, Lisa, on the right, what is the x-axis? Is that time?
Yes.
Okay. All right,
Sorry.
So that's accumulated.
Sorry. Yes. There's no.
Okay. So that's the time series, and the trends are like the integrated effect, right? Like
the cumulative.
Yeah.
Yes.
Yeah, okay.
Integrated over time. Yes. Exactamundo. Sorry about that. Yeah. This should say time.
Is it the whole 30 years?
No. This is just 2 years. This is 2 years. So this is in situ data. This is the second array that had the velocity, the temperature, and the salinity. This is all in situ now. Okay, so these cumulative fluxes are very small. How do we know they make sense? Well, you might have got an inkling of that already if I'd drawn those circles the right way around, but... All right, so I roll up my sleeves for this. Hopefully I can explain it well enough and have it straight enough in my own head. Okay, so we wanted to go back and look at the flavors of these eddies to make sure that, you know, these eddy fluxes made sense. And one of the ways you can do that is you can look for barotropic and baroclinic instability by calculating some kinetic energy conversion and potential energy conversion terms in this way. For instance, Donahue et al. 2016, for example. And what does that mean? Barotropic instabilities are driven by shear in the flow, velocity shear, horizontal velocity gradient. Okay? So this is a kinetic energy, a mean kinetic energy to eddy kinetic energy conversion. So when is the mean kinetic energy of the flow feeding the eddies, right? And then the baroclinic term is the potential energy term. So this is driven by the gradient of density. So if you imagine with the current, you've got more dense water sitting next to less dense water. And if you have fluctuations in that could become unstable. The less dense wants to move on top of the more dense, right? This is your classic baroclinic instability, driven by horizontal gradients in density. So this then is your kinetic energy terms, eddy to mean, mean to eddy, eddy to mean. So this would be stabilizing the flow in blue, and in red, growing the eddies, right? In blue here, stabilizing, and in red, growing the eddies. Baroclinic, barotropic. What we start to see is, and the red is, yeah, I said that. The red is mean to the eddy, mean to eddy, and the blue is eddy to mean, okay? What we start to see is that we have these times, and the gray line here is the distance offshore of the velocity maximum. So we're starting to see, and what we've got around these boxes is these meanders. Okay, so let's look at a meander case. What is happening? So a meander is a solitary meander of the current like this. It has a scale of about 100 kilometers across, and it's going to have the pattern of an inshore low and an offshore high. And what's happening is, if we take this one case, right, and we'll go to the baroclinic first, we'll see that as this instability propagates, and this is propagating downstream at about 15 kilometers per day, something like that, as it propagates onto our mooring line here, we see this burst of energy, potential energy to the eddies, right? And once we're past the trough here, we see a lot of that energy feeding back into the mean flow. At the leading and trailing edges of the meander, we see barotropic instabilities. So now you start to see a pattern of positive, negative, positive, right? Positive, negative, positive, positive, negative, positive. So what you're getting is you're getting energy feeding the eddies on the trailing and leading edges, on the leading and trailing edges of the meander. What's happening here is you're getting convergence and divergence. So this flow is a lot faster than the meander propagation. So the water is pouring in to this cyclone, right? And it's decelerating around the cyclone. You've got a lot of convergence, and that convergence is driving this barotropic instability. It's also driving the propagation of the meander itself. And at these points, that's where you're going to get this rush of energy from the mean shear of the flow to the eddies. what we also see is that when we haven't got these huge meanders, we have got other instability processes going on. And so in this relatively quiet period, when the current is always attached to the coast, but now what's happening is we've got these much smaller scale instabilities going on. They seem to be dominated by baroclinic instability processes. You can see how we've got a lot of red here, where there's a feeding of energy into the eddies. And oppositely in the barotropic, we've got the opposite. We've got the eddies feeding back into a mean flow. And so this is happening whenever we have these smaller scale eddies. You'll see that they don't often have an imprint, or hardly ever have an imprint across the whole array, right? It's just instabilities going on at A and B. Okay, so those are frontal eddies. Frontal eddies have been observed many times before, although they're kind of difficult to observe because they're such small scale. Here's one inshore of the Agulhas Current in some drifter tracks. Here's one inshore of the Gulf Stream, right offshore here, from some of Nick Shea and Matt Archer's work 10 years ago. So now this is measured with the HF radar. And you can see these little frontal eddies inshore here, right? So if we look closer at the PE conversion, the baroclinic energy conversion term, at just A, that inshore front, then we can see all these red dots at times when there are baroclinic instabilities. There are these inshore frontal eddies. So we have barotropic instabilities associated with the meandering jet, seem to be leading the show, and then we have baroclinic instabilities associated with the linear jet, if you like, just these small kind of wobbles of the inshore edge of the jet. Okay. And if we look at the eddy fluxes again, we can separate them into the linear case and the meander case, and we can see that in the linear case, this is with the frontal eddies, they really dominate this offshore warm and salty fluxes. Okay, so these smaller frontal eddies, which surprise me, perhaps it doesn't surprise you, but they actually dominate the cross-shore eddy fluxes inshore of the jet. So that implies that these submesoscale eddies are dominating the cooling of the adjacent shelf seas. And then offshore, it's the meanders that are dominating the eddy fluxes, right? And in that case, they're moving warm, salty water onshore. So the meandering jet is moving warm and salty water onshore. Okay, this is what I hope I've... okay, so we can look at then in the mean. So hopefully we're kind of confident that these calculations are showing us something real, even though the tendencies are rather small, right? Over 2 whole years, we got tendencies that are about the size of the standard deviation of the fluxes. But they seem to make sense in terms of what we understand is happening, the instabilities in the current. And so if we look at the eddy fluxes in the mean, we get this picture. So this is up over the upper 1,000 meters. This is temperature, this is salinity. The yellow is salinity onshore, the red is temperature onshore, the blue is temperature offshore. Okay. So what you're seeing is that mean center of the jet at B, we've got the eddies fluxing temperature and salt onshore on that side of the jet, right? And this eddy flux is dominated by the barotropic energy conversion. You can see in red are all the positives, right? Positives is the mean to the eddy, right? Then on the cyclonic side of the current, right next to the coast and right over the sloping topography here, we have fluxes in the opposite direction. We have eddy fluxes towards the center of the jet, and we can see that over here, the baroclinic component is dominating the eddy flux, the eddy fluxes. If we think about it in terms of what these energy budgets are telling us, then it means that on the offshore side, these eddy fluxes are a result of eddies draining the barotropic flow and feeding the baroclinic flow and warming the jet core. So that means that they're draining the barotropic flow. That means they are decreasing the horizontal gradient of velocity across the Agulhas current. So that's back to this broadening idea, right? At the same time, though, beyond what we could tell from the satellite, the baroclinic flow is being fed by the eddies. What does that mean? That means that warm salty water is being moved towards the core of the jet, and so the density gradient is increasing on the offshore side. At A, over the slope, the eddies are draining the baroclinic flow. So the density surfaces are actually slumping there, right? And this is cooling the shelf waters. And there's an update to that with the barotropic. So the barotropic flow, you might remember, was negative. So there was a feeding, and I should have updated it. There's a feeding of the barotropic flow over here. So the tendencies in terms of the density gradients and the velocity gradients are the exact opposite, one side to the other. The velocities gradient will tend to be sharpening here and relaxing here, and the density gradient will tend to be slumping here and sharpening here. Woo! Okay. What's happening over the slope is consistent with eddy-driven upwelling on the slope and downwelling above. This is important for thinking about, okay, this is just the Agulhas current. You said all the subtropical boundary currents, right? So eddies interacting with topography can drive upwelling on the slope and downwelling further offshore. And this follows turbulence closure theory, which I never thought I would say in front of Tamai. He's going to say, hopefully I understand. Where basically you can show that the work done by eddies on the slope will give you this upwelling, provided you have negative topostrophe. This is in terms of topostrophe. If you don't like topostrophe, you can also think of Ekman veering. So if you think about if you think about just a bulk parameterization of the eddies, then you might think of this as Ekman veering, right? So if I have a current coming at us next to this slope in the southern hemisphere, that's like this little cartoon here from Schubert et al., who just have a brand new paper out about, actually they're talking about downwelling, because they're talking about the bottom of the ocean and how you get downwelling by the work of the eddies on the slope. Up here in the thermocline, and I'm going to argue therefore inshore of every single subtropical western boundary current, right? where in the southern hemisphere we have the current coming towards us, we could flip it and say, look, we're in the northern hemisphere and we're thinking about the Gulf Stream, right? Same thing. This work of the eddies on the slope is going to give us upwelling. So that implies that the eddy fluxes will have the same tendency in all subtropical western boundary currents globally. It could be, I was thinking about this, and you might say all subtropical boundary currents, but that might be a little dangerous because the friction may not be a dominant term on the eastern boundary, right? So I pulled back from saying that. But anywhere that you've got cyclonic flow over the topography is going to give you upwelling. Okay. All right, so then the Agulhas Current appears to be eddying more. And we even checked it recently and it's still eddying more. A lot of subtropical western boundary currents, when you start to think about tendencies, is really tricky because you've got a lot of decadal variability. I think we're lucky in the Indian Ocean that we don't have a whole lot of decadal variability. Decadal variability is much smaller than other ocean basins. I'm not quite sure why that is, but I have a theory, so maybe somebody can work together with me on it. So the Agulhas Current appears to be eddying more with a weaker transport in its core, compensated by a stronger transport at its flank. The eddying reduces the total meridional heat flux of the Agulhas Current while increasing the surface temperature flux. So that's this idea of like a more stratified boundary current that can both carry much warmer surface waters but less heat transport overall. On the anticyclonic side of the current, the eddying extracts kinetic energy and adds potential energy, meaning there's less velocity shear but more density gradient, sharpens the density gradient in the Agulhas Current, by fluxing heat and salt towards the jet core on average. On the cyclonic side, over the slope, the eddy extracts potential energy from the Agulhas Current and cools the adjacent shelf waters through eddy-driven upwelling and overturning. Okay. And finally, I'm going to argue that through turbulent closure theory, then, this suggests the exact same tendencies for all subtropical boundary currents where eddies are increasing. And there's more and more evidence that, indeed, eddying is increasing. In the East Australian current, there's a few papers talking about it. Even in the Gulf Stream, there's a few papers talking about it. In the Kuroshio, it's a little bit tricky because it's in this kind of giant meander state at the moment, further downstream from where it separates. But people are saying, why is it stuck in that state? You know, it's kind of in this permanent big meander, which means it's arguably meandering more. But there's a lot more decadal variability there. So I'll finish there. Hopefully I've
Thank you, Lisa. Are there any questions in the room? To mine.
Very nice talk, very mysterious. I have a question about the cyclonic side where you said you saw some submesosphere eddies. Did you, since you have 2 years time series, did you see any seasonality in the formation of the small eddies?
No, because they're not mixed layer eddies, they're frontal eddies.
And then the second follow-up question is that how does it interact with the upwelling? They are all aligned, right, on the same. Do these eddies interact with the upwelling that you close with?
I'm arguing that they cause it.
They cause it up. That part, not the whole curve.
those sub-mesoscale frontal eddies.
Oh, okay.
Yeah, I'm not arguing that they cause it.
Okay, great.
Yeah.
Amy?
Yeah, thanks, Lisa. So fun to think about the ocean. It's so messy. I wanted to follow up. So would this mechanism suggest shelf waters should lose a cooling trend?
Yeah.
Which is not what's observed, though, at least like in the North Atlantic.
Well, okay. It's not what's observed at the surface. So it's very hard to kind of cover it. But this upwelling is often what some people have called cryptic. In other words, you can be flushing the shelf with all this cold water, but above it is warm water. It's stably stratified. And so you don't necessarily see from space that cooling. So what I didn't go into is, this suggests, right, that the current itself, and if it is eddying more, is cooling. But at the same time, of course, you've got global warming, and shelf waters are going to be heated from above. And so I suspect that the implication is stronger stratification over shelf waters, cooler at the bottom and warmer at the surface.
I can't remember, but there was all that work on the shelf in the North Atlantic. I thought it was the whole shelf warming because the lobsters were, living at the bottom were really impacted. The lobster population was impacted. Maybe that's different.
Well, so another thing you should be careful of is that might have been after the Gulf Stream separation.
Right.
So you're right.
Yes, definitely.
Yeah, yeah. So then, bets are off because you don't any longer have these eddies working on the slope. So so there could well be different things going on there. And in fact, you might have downwelling because if you're into the subpolar gyre, then the topography is opposite. So you kind of get the sense that the subtropical gyre is keeping more heat in the middle, and it's cooler around the edge. You get a sense of an intensification of the gyre in terms of the density gradients. But it's not playing out in terms of the total transport. Yeah.
Yeah, it also, another complicating issue is if you don't have enough complicating issues, is the depth of the shelf break, because that may play into this game.
It may, but the theory predicts that you're still going to have upwelling.
Yeah.
Unless at the point at which you get an undercurrent. I mean, this theory predicts undercurrents in western boundary currents, which I wish I'd found it many years before, because back when I was a student, I was doing undercurrents, and I was like, why is this undercurrent here? So at some point the friction backs the flow.
Yeah.
And then you've got downwelling.
Yeah.
But I don't think it matters the exact shape of it. I mean, it probably matters the amplitude of it, the amplitude of the effect, maybe, or how far the upwelling reaches in the shelf. Because you might also imagine that the near shelf, the near coast would be warmer.
Yeah.
And you get this kind of Goldilocks zone, at the shelf break, where you've got this upwelling of cooler waters keeping it refrigerated.
Yeah, there's some extreme examples of that off the coast of Africa. Very, very wide shelf, very shallow. This complicated system, to say the least.
Yeah.
We have a question on Zoom from Alex. If you could unmute yourself.
Oh yeah. Okay, Lisa.
Hey Alex, good to see you.
Yeah, you did fantastic work at your colleagues, mostly with Agulhas Current, but applications to Straits of Florida, congratulations. We've been at the Oceanographic Center NOVA, been involved for some years in studying something maybe different, but we've been seeing this type of phenomena. And 1 year ago, about 2 years ago, we did annual overview with gliders, local gliders from Fort Lauderdale to Jupiter, and we did see upwellings, we did see eddies, and we did see undercurrent jet attached to the continental slope, and that now I see lots of details which we didn't understand, but now this is a kind of general theory and observations we can apply to that. And also recently I saw in the literature people call this hidden upwellings on the western boundary current, when they come really to shelf, contribute to corals health, but they are not seen from space because they never penetrate through the surface, to the surface of stratification. But what we observed with gliders during winter time, these upwellings do propagate to the surface because stratification is weak, and that's a very interesting direction here in Strait Florida. Yeah, so that's great work.
Cool.
Thank you.
Sounds like you need to invite me up for a visit so we can talk more.
Yeah.
Do we have any more questions? No? All right. Well, thank you again, Lisa.
All right.